Hello everyone, this is Miao Chen. I will do the presentation for our group about the CPU we designed. Our group members are Zhao Huiye, Miao Chen, and Lin Haoxue. Since NYU has developed an open source RISC instruction set, so the problem we solve is to design a processor to execute these instructions. There are three main instruction types: computational operations, load or store between memory and register, and control flow like branch instruction. To achieve that, referring to existing CPU structure, the CPU hardware should be like this. It has a PC block, register, memory for both instruction and data, ALU, and a lot of logic gates. It is fine to design exactly at this way, but we decide to optimize it, so we summarize 6 main blocks. A PC block, handle all PC stuff. An instruction memory block, handle all instruction stuff. A register field, handle all register stuff. An ALU block, handle all arithmetic and logic stuff. A data memory, just save data. And a control unit, which is the most important part and the most outstanding part of our design. It will control all the control signals and the program running process. And this will be our final diagram of our design. Since we do not run instruction in pipeline, so we use a finite state machine to control the running of the instruction. For different kinds of instructions, it will use different blocks in different order. For example, an addition instruction will read instruction memory, read register, and ALU do calculation, then write back to register and update PC. A store instruction will read instruction memory, read register, ALU do calculation, then store in data memory and update PC. A load instruction will read instruction memory, read register, ALU do calculation, load from data memory, then write back to register, then update PC. So no matter whether the instruction will use the block, the order for all instructions should be PC fetch and decode, read register, ALU calculation, read or write data memory, write back register, update PC. So our finite state machine contains these 6 states plus 1 state which is idle state. The idle state is simple. When the CPU runs halt function like eCall and eBreak, or the reset signal is active, it will get into the idle state and do nothing. When the reset signal deactive, it will go into the instruction fetch and decode state. As I said, the control unit will change control signals. Let's say a load instruction. The state will go into next state where it meets a rising edge of clock. In cycle 1, the control signals like read IM and select data x10 will change to the corresponding value. In cycle 2, the read register goes high since it will read from the register. In cycle 3, the ALU is doing the calculation. In cycle 4, the MCDM will change to the corresponding value since it may load bat or load word or load half word. Then the cycle 5, it will write back to register, so WREG will goes high. Finally, cycle 6, update PC, so the WPC goes high. And this load instruction just finished. This is exactly how the CPU works. For the ALU part, it will calculate these two values decided by the instruction. It will do the read calculation by these control signals that the control unit gives to him. Except this select signal for this mux, our ALU has these control signals like OPBC, OPX10, and OPALU. We do an encode for the possible instructions, so the ALU can know the instruction with the least signal bits. The PC part is simple. It just do the PC update with the instruction memory. And the instruction memory and data memory are simple too. They are just two arrays of words where the IM will decode the instruction and DM will store data or load data out. And for the data memory, it also has some control signals to control read or write memory and controls the length of the data to read or write. Last is register. Register is similar to the memory, where the register has only 32 words. We test our design by two programs. First is insert sort program. Since we have stored our n number in memory, so we break them into 12 numbers and save them in the memory. And then we do the insert sort. Another program is RC5. We store SKs in the memory and store two values in the memory at the input of the RC5 program, which is 64 bits. Then it will encrypt first, and then they decrypt it back. By these two programs, we have tested all kinds of instructions, including shift, branch, load, store, and so on. And this is an overview of our test bench result. And talk about outstanding parts, the first thing I want to say is the block optimization we made. We use only 6 blocks, where each block has more function than a single logic unit, especially the control unit. It controls the whole process of running instruction. Also, we do some encode for these control signals, so we use less control signals. Of course, our design still has space to optimize. Since by our finite state machine, the CPI will be exactly 6 for all instructions. Actually, people can design a more complex finite state machine to decrease the CPI. And that's all I want to present. Thanks for listening.